Well, thank you everyone for coming. I guess there's a march today in DC, so some people are delayed. I didn't know about it. But I'm really looking forward to today. I think it's going to be a really interesting morning, and I think we'll learn a lot. Why are we here today? Why is Hudson doing this event about fusion energy? Well, the bottom line is today's energy systems can't keep up. Fusion energy offers the possibility of a breakthrough in clean, sustainable energy. Fusion power plants in the future will recreate the same reaction as the sun and capture that power so it can be distributed safely, sustainably, and affordably. Now, I know there are debates in the scientific community and in the community writ large, but in 2022, the U.S. pulled off a historic first fusion ignition, producing net positive energy at the Lawrence Livermore National Ignition Facility, or the NIF. 93% of American fusion companies believe fusion power will reach the grid on or before the 2030s. And there are about 25 of these companies in the US, I think about 45 worldwide, based on the Fusion Industry Association. The same Fusion Industry Association has pointed out the U.S. private sector has put some $8 billion into fusion energy. I think that's also probably surprising to a lot of people, maybe not those who follow the issue closely, but also not surprisingly, China's catching up. It's putting far more public money into fusion, something like $1.5 billion annually toward the effort. Moreover, it has an ecosystem approach to fusion. It's building a big campus in eastern China with a new generator, access to workforce. China has now more fusion patents than any other country, 10 times the number of doctorates in fusion science and engineering. So there's a competition there. The reason we're doing this at the Hudson Institute is to think about what that competition means, both in terms of nuclear deterrence and how fusion fits into that. And the first panel will address that. And the second panel, my panel that I'll moderate, will look at the commercialization aspects of fusion. So we're not going to debate the science today, and that might make some people uncomfortable. What we are doing is looking at those two aspects of fusion energy as assumptions going in, and we look forward to the day and to the questions from the audience. I'll turn it over to my great colleague, Rebecca Heinrichs, who's head of the Keystone Defense Initiative here and an expert on strategic nuclear issues and many more issues. Thanks, Rebecca.
Thanks, Nadia. And thank you all for joining us in person, and those of you joining us online, welcome to the Hudson Institute. My name is Rebecca Heinrichs. I am a senior fellow here at Hudson, and I'm the director of our Keystone Defense Initiative, where I focus on strategic deterrence and nonproliferation arms control, and then national defense broadly. But it's a real privilege for me to be able to moderate this panel. I do a lot of thinking about our adversaries' nuclear weapons programs, and how the United States might successfully collaborate with our allies to adapt our own deterrent to deter the many different adversaries. For the first time in American history, we will be seeking to deter two major nuclear powers simultaneously, not just one, as we did during the Cold War. Now we have, if the Chinese continue on their current trajectory, we'll have China and Russia to contend with in the next, within the next decade. And the last, I guess it's two STRATCOM commanders now ago, Admiral Chaz Richard was the first to coin the phrase strategic breakout, that China was in the midst of a strategic breakout and was investing a lot of effort in its nuclear weapons program and was going from what we understood to be a credible minimum deterrent to something much different. And so it's a privilege to be able to talk about what it is that they're doing technologically to make that possible. So I've got three distinguished experts to help us think through all of this. I'm not going to go over their bios in an exhaustive way, but we do have Jimmy Goodrich. He's going to go first today. He's a leading scholar and expert on Chinese and East Asia technology, geopolitics, and national security. He's a senior fellow at the University of California Institute of Global Conflict and Cooperation, the IGCC, and he's a consultant to the RAND Corporation. And then after him, we'll have Keith Leshien. Did I do that right?
Leshien.
Leshien, okay. Dr. Leshien currently serves as the founder and CTO of Pacific Fusion, a position he has held since 2023. And before assuming this role, he held multiple significant roles throughout the science and technology sector, including as the principal research scientist throughout the science at Tech Lead at X, the Moonshot Factory. So really thrilled. Oh, I see you're at Lawrence Livermore National Lab as well. Thrilled to have him with us. And then to close us out here, to think about what the United States is up to at Sandia, we have Dr. Daniel Sinars. You got my Midwestern accent given a shot. He's the Deputy Chief's Research Officer and Managing Director for its Chief Research Office. And so we're thrilled to have him with us today. It's a privilege to have you. And so what I'd like to do today is just ask each of these gentlemen to give a few moments of opening remarks to get us thinking about this, and then I will help facilitate a discussion among the four of us, and then we'll leave some time for you all to ask some questions at the end. So with that, Jimmy, the floor is yours.
Well, thank you, Rebecca, and thank you, Nadia, and the Hudson Institute for putting this important discussion together this morning. Look forward to sharing my thoughts about what China's up to in the inertial confinement fusion space and what that means for our national security. So you talked about China's strategic breakout, and the Department of Defense estimates that by 2030, China will be building up to 1,000 new nuclear warheads, have entire new delivery systems, air, sea, and also we see that build out happening across the country, whether it's the missile fields in Western China, its missile production network, all sorts of new breeding reactors. So they're building up this massive infrastructure to support that strategic breakout. And what Xi Jinping has called for is a strengthened nuclear deterrent and counterattack capability. That's the guidance he's given to his rocket forces. And even after all the impressive buildup that we've read about in the New York Times, the Wall Street Journal, see all the satellite images, Xi Jinping is not satisfied with the pace and scope. And last October at the National People's Congress, he said China needs to even run faster, accelerate quicker its nuclear deterrent capabilities. So one really important piece of that, and what we're here today to talk about, is where the science, and particularly the science of fusion, fits in and supports the nuclear weapons deterrent capability. Since the early 90s, with the comprehensive ban on testing, the United States and other nuclear weapons powers have used computer codes on supercomputers, coupled with fusion experiments using something called inertial confinement fusion, where you're compressing pellets at very high temperatures with either pulse power or lasers. And that's now the Laser Ignition Facility, the National Ignition Facility out at Lawrence Livermore National Lab, and the Z machine at Sandia that Dan and his colleagues run. Those are really, really important for the United States to assure our stockpile. So China, not surprisingly, and I published a paper recently through UC-IGCC, is on a crash program to build out a massive ICF program. Thank you. And part of that is a large secretive laser facility in Western China, located at their nuclear weapons laboratory. They've made no public mention of this facility, but it's visible from space. It's huge. It could likely be 4 times the size and output of the National Ignition Facility, which will give China, incredible capabilities for modeling the effects of nuclear weapons and for understanding how to accelerate the pathway to commercial fusion. Another part of that is pulse power, and that's using electrical charges to create the same type of confinement fusion reaction. And China there is building multiple new pulse power facilities that will be, likely, if we don't get our act together, much larger than anything the United States has today. And so I wrote up these findings in this paper. They're very important. The central government has really spared no expense and is moving at breakneck speed to build out these facilities. For example, the China Academy of Engineering Physics that's hosting, which is basically China's Los Alamos and Lawrence Livermore combined, is hiring 2,000 engineers just over the next couple of years to support all of these new facilities and programs. So this is going to give China tremendous capability, both on the civilian science to understand everything from astrophysics to fusion energy, because recreating the conditions of hotter than a sun helps in many different ways, but it will also help China strengthen its nuclear deterrence, be able to build stronger materials for shielding against radiation effects, hardening all their systems against electromagnetic pulse, and simulating and verifying some of their codes to ensure that their next generation warheads designs that could be lighter and higher yield and more potent actually work. And so this is very important for China.
That's great.
Yeah. So Jimmy, you touched on this. One of the, and I met Jimmy when he first reached out, 12 months ago to talk about, what China's doing and showed some of the impressive buildup in this area. they're moving incredibly fast. You can open the paper every day, there's a new major advance that through building infrastructure, AI, quantum, and now fusion, that China's advancing incredibly quickly. The US is the home of much of the fusion science and technology that's been invented over the last several decades, and that's been through government investment. Many tens of billions of dollars since the 1960s has gone into investing in fusion in the United States. And yet we're at this moment where we're now watching China take the science and advances of that US investment and turn it into action and actually surpass us in capabilities. I don't think it's appropriate to say, oh, we won't keep up or something. I think it's that we're already behind if you look at the speed at which China's building in this area. And one great example in the last 20 years where the United States was also in a strategic disadvantage and wanted to stay ahead was in the space industry. What did it do? What it did was it stood up a public-private partnership program called NASA COTS through the Space Act that ultimately, from that SpaceX was born, right? We wouldn't know what that is today without that program. And now today, amongst other industries, China's intimidated by our space program because of these investments. It took 20 years to play that out. We're at that same moment today in fusion, where the amazing work at the national labs has set up the conditions to position the United States strongly, both in energy and for fusion related to defense activities. But we can't move fast enough without that kind of additional investment and additional partnership between government and industry. So I think I'm here today. I spent time at the national labs, now founding Pacific Fusion with our team. And I see the definite strengths that the government brings to this strategic area of fusion, but also where it can also kind of stall in terms of investment and infrastructure build out. That's a very unique opportunity for industry to pick up. And we're at that moment right now.
Thanks. No, I think, Keith, that's a great point. We were chatting about this before we came on stage, and you had made that point that we talk so much, and we do a lot of work here at Hudson too, at examining what the U.S. has underinvested in over the last 40 years and have done wrong and how we need to play catch up. But it's good to see things that we did right so that we can duplicate them. And your point about it's a SpaceX moment for NNSA, and that we need to look at how we did that to invest in the same way.
And just adding on that, the Chinese talk openly about how they are behind in space capabilities. Obviously, they're trying very hard. They're investing a lot. But the U.S. has this huge launch capacity lead that would not be there without SpaceX and the COTS contracts. And so, we want to put ourselves in the position at the end of this decade where the Chinese are envious of what we've done and we're far ahead, leveraging the public-private sector, government companies combined.
Make Xi Jinping envious again.
Yes.
It's a good slogan.
Trademark that.
Yeah. Daniel, the floor is yours.
Let me just clarify, when we're talking about fusion, there's a wide range of fusion energy technologies out there. And so I know the next panel has a speaker from Commonwealth Fusion Systems. So that's in what we call the magnetic fusion domain, which is very low density plasmas, very long confinement times. What we've been talking about here is things that are very high density, very, very short-lived plasmas. And those are important because they can replicate the conditions produced in a nuclear weapon, in the nuclear explosive package, or produced by a nuclear weapon in terms of the radiation outputs of a nuclear weapon. And that's why the inertial confinement end of the spectrum, very short time pulses, has always been relevant to defense programs in the United States and has been funded by the National Nuclear Security Administration. So the history of the interest in fusion on the inertial confinement side dates back to the dates even before we ended underground testing. And since the end of underground testing, the United States has not done an underground test since 1992, we have turned to our high energy density facilities or our inertial confinement fusion facilities for a lot of the research and development to study the phenomena, again, produced in a nuclear weapon or by a nuclear weapon. So it's been a tremendous asset for stockpile stewardship science, and to the point where we're now pivoting in our national defense strategy and looking to potential development of new nuclear weapons. Ultimately, it's going to play a role in that as well. And the importance of this with respect to China, if you look at our history, we have far more underground nuclear weapons tests than any other nation. In fact, all the other nations combined, more or less. And what that gives us is we have been able to test a wide range of weapon concepts and phenomena underground. We've been able to collect a lot of fundamental data that goes into our weapon codes to do simulations with high accuracy, high fidelity. And the opportunity presented by having these strategic assets, like the National Ignition Facility or future HED facilities and fusion facilities, is that you can collect a lot of that data without needing to do an underground nuclear weapons test. And so this underpins a lot of China's interest in these facilities, is that they know that even though they have resumed at least some form of underground testing based on the comments made this week, they certainly know that in the long run, you could get a lot of this data far more efficiently and cheaply with a laboratory-based source. So a tremendous opportunity here. I agree with this. It's kind of a SpaceX moment. We have the success of decades and billions of dollars of investment by the NNSA in the National Ignition Facility, demonstrating that ignition is possible. And now we'd like to build on that, both for national security and for national prosperity in terms of fusion energy. And the question is really, in my mind, not whether we should do that, but how we should do that most efficiently in this nation to keep us in the forefront of the world. And so the NASA COTS example is a fantastic example of one way to do public-private partnerships. And so most people have heard of SpaceX. SpaceX got its launch by collaborations with the National Aeronautics and Space Administration through that COTS program. And so there are opportunities for public-private partnerships where we could collaborate and do a lot of work that benefits both our national security and our national prosperity. If I could delve technically just for a moment, if you look at what we would need to do with a pulsed inertial fusion capability, most of the private pulse companies are talking about yields in terms of about 100 megajoules to a order of a gigajoule, maybe a few gigajoules. So a gigajoule is a quarter ton of TNT, so these are not small explosions that we're talking about in a laboratory setting. And they would need to do yields of this size about a tenth of a hertz to 10 hertz, depending on the particular concept. For the NNSA missions, the goal since the 1980s has been to achieve what we call high yield in the laboratory, which is yields of a couple hundred megajoules and higher. And we would not need to do that many times a second. We would be content maybe with once a month, as long as it was a very highly diagnosed, precision-controlled laboratory experiment. So there's a lot of overlap then between what the private fusion sector is trying to do in terms of the yield and what the NNSA has been trying to do for decades. And with that, the technologies to do that, the technologies to create those conditions, the technologies to diagnose those conditions, tremendous synergy with what the private sector might want to do and what the NNSA has been trying to do. The deviation is largely in the repetition rate and the level of fidelity by which you need to understand those conditions. So I'm a big fan of trying to look for ways where we can partner so that we can go faster. I think it's with the private fusion sector, we're far more likely to get capabilities in the laboratory than we would if the NNSA was left to its own devices. And so I'd be tremendously excited to see that. And maybe that's one of the strengths that China has had. Dictatorships are always very efficient, and then they can very efficiently walk them ways down off of a cliff. So that's the downside of dictatorships. But we have succeeded as a country largely through public-private partnerships, and there could be an opportunity to do a lot more there.
Great. So I do want to talk about how the models of our two governments create, in one sense, an advantage for China, disadvantage for the US, but that we do have a great advantage, and that's why collaboration between the labs and then also these private companies is the way to go, and that we have to do it. So I do want to talk about that. But so before we kind of talk about some of those ideas and solutions, Jimmy, can you talk, because your paper does talk about how that has been how China has been able to go so fast. And this basically, they're indistinguishable between the private sector and public sector within China. When did that start?
Yeah, that's a great question. So actually, we saw right after the United States announced net gain ignition on the NIF, China started building rapidly their facilities. So basically, we proved the science, they're building it out and making it a practical thing for both their national security mission and for fusion energy. But obviously, China has also put all this in their 5-year plans. And so in the most recent 14 5-year plan, they're now going to announce the 15 5-year plan this spring. But they included, for example, pulse power for inertial confinement fusion in their 5-year plan for the last 5-year segment. So this is a top priority for them. They're moving very quickly. They have sort of government determination It's also a very interesting time as many of the people that are at the leadership level responsible for this are either under investigation, disappeared, or missing, or for anti-corruption investigations. So that's also one of the pitfalls of China's system is personnel is very unsteady, particularly within China's nuclear enterprise. There's a lot of personnel change. But the pace of these projects, you can tell they're a priority, has really not faced any setbacks. In particular, I talked about they also have a diversity of programs. So they're not just pursuing one approach, they're pursuing multiple different laser fusion projects, multiple different pulse power projects. And in the United States, we're largely doing that too, but it's the private sector. Within China, the big difference is these are government labs, civilian and military, that are conducting the research. There are some startups in China. They're mostly in the magnetic confinement fusion space. There is one or two in the pulse power space, but they have deep government connections. So, I would argue that our sort of more entrepreneurial free capitalist system is going to be more efficient. But because there's this valley of death around innovation, and if we don't support the commercialization of it, particularly for the national security mission, I worry that China will get there first because they're so determined.
Great.
And I did want to add, at least in terms of I think there's tremendous opportunity here. The downside of that intimate connection between what we're trying to do with private fusion and national security is that we used to classify the entire inertial confinement fusion program in this country for a reason, right? Which is that it does have close connections to our nuclear weapons technologies. And so there's a fine line to be walked here in terms of how we want to work and partner between the private industry and the federal government. We spend tens of billions of dollars on non-proliferation work across the country, and across the globe, and that's a sign that we do treat nuclear technologies a little bit differently than like the F-35 fighter or something like that. And it's really not even the driver. Like we've talked about pulse power, we've talked about lasers. It's again, what you can do with the technologies. It's what you can do with the simulation tools that we have. So we spent decades building up these exquisite models. It took us over a decade to achieve ignition on the National Ignition Facility because our finely tuned models were not quite right yet. And we spent over a decade learning about how to tune those models and what we didn't understand. And ultimately, that needs to be protected at some level. And from a proliferation point of view, there are dozens of companies out there. There are 3 national labs that are working on this today and within the NNSA. How do we appropriately expand the use of these technologies to benefit the national prosperity through fusion energy while maintaining control of technologies that could be a proliferation risk?
Right. And I did want to, you had mentioned, you had referenced the breaking news that came out last week, the recently declassified, I guess, information from Undersecretary Donano about China's nuclear testing. So that's what you were referencing that came out. I think he was in Brussels when he gave that speech last week, or he was somewhere. He wasn't here.
It was in Geneva, yeah.
He was in Geneva, okay.
Geneva, yeah.
And so just again, emphasizing just the priority that China has placed on this. And I mean,
it's, it's also part of China has a goal to be the global scientific leader in all domains. It's not just fusion, it's chemistry, materials science, physics, biology, and they're building dozens of science facilities across the country. And so this is just part of a massive science breakout for China. But within this, we're focused on the nuclear side, but I mean, China is building the equivalent of these type of facilities in almost every domain you could think of.
yeah, you had mentioned China's goal in your paper here of technological, I think, autonomy or self-sufficiency. I don't know what the
Yeah, I mean, many Chinese researchers had used U.S. facilities previously.
Right.
Obviously not those at NNSA, but for example, the SLAC particle accelerator at Stanford was used by a lot of Chinese researchers for their semiconductor program. Material science for China's aerospace program was done at some of our other national labs and facilities. And since those have rightly more limited access or ceased access, China's been building up their own national science ecosystem. And nuclear weapons science is definitely a top priority amongst that. Military, civil fusion, and China's strategy of fusing civilian and military capabilities is definitely prevalent across many, not all, but many of their new science labs.
Right, and that seems to me to, at least the way experts kind of talk about what China's doing, even 5, 6, 7 years ago, when we looked to see what China was doing technologically across fields, a lot of people sort of credited the United States. They stole the technology, or they got the technology, or many of these scientists are still educated in the United States and they go back to China. But it's changed where they're doing, a lot of this is just inside China where they're becoming independent. And then we were also discussing there how that creates problems for the United States to try to counter it or to slow it down, because there's not much we can do maybe in that. I don't know if you want
Yeah,
to
I mean, there are areas where the United States has a lot of leverage still, like in semiconductor manufacturing equipment or in advanced AI chips. Much of the technology for, and Dan and Keith can talk more at length about this, but whether it's the glass or lasers or the capacitors that go into these type of systems, China has a very strong indigenous capability, and they've been able to build out, very comparable systems. And the risk for the United States will be that, China will not be replicating or imitating. We will be very jealous and will want to know what they're doing because they'll have science and physics facilities that can, as Dan mentioned, model in the 100 megajoule range where we cannot. And we'll be just kind of left trying to peer in and understand what they're doing if we don't build similar type of facilities. And that will, as we talked about, enable China to both commercialize fusion much quicker, but on a nuclear deterrence perspective, be more certain that their arsenal will be as potent as they can make it.
Keith, you had mentioned here that Congress recognizes the importance, that there has been some progress here of Congress paying attention to this in particular. Can you talk to us about Congress's interest, or you have here it's $10 million. That to me doesn't seem like that seems like couch cushion change, congressionally speaking.
I won't comment on how big the couch is, but no, I think fundamentally it's about time, right? And when you talk about what the government did in this, to launch the private space industry, right? It was determination. Some administrator of NASA said, we have to do this. Our costs are too large to do this the way we've been doing it. It takes too long. We want to win. Administrator Michael Griffin made the decision, we are going to launch this program and it's going to be run through industry working, of course, with the NASA laboratories and the government infrastructure. Fast forward 20 years, we're now, going back to the moon, right? And this is, a direct outcome of that partnership launch 20 years ago. We are at that exact same moment here today in fusion. And Congress does recognize that. This is an issue that is, incredibly nuanced. It takes a long time to sort of understand all the, trade space of where energy and defense meet fusion. But so that appropriation that we saw this cycle through the energy and water bill is an enormous step forward in that recognition that we have to, specifically calls out public-private partnerships. It specifically calls out technologies that can actually be delivered this decade. And it's the start to that conversation, and it enables the requirements of the agency to align to what private industry might otherwise be doing. Here's an example. Imagine if COTS hadn't been launched, yet there was a SpaceX. That was true. What if SpaceX had built rockets that were a few inches too small to carry the payload that was most interesting to NASA to launch years later? That would have basically been a wasted effort, because then that thing that was made would not actually be able to be used for the requirements that NASA had. That alignment up front of what the requirements are with what industry is doing makes a huge difference, especially on this time scale that we're talking about. We have massive capabilities we're delivering by the end of the decade. It rivals what China's pushing on. Yet right now, until this recognition by Congress, there really wasn't a forum to align the types of requirements that the Department of Energy and NNSA might have in this defense fusion mission with what we were doing. So it's a huge step forward. It's just the beginning.
And if you look at the NNSA's public roadmap, obviously they're very focused on building new warheads and pits. And that's an important mission that they have, upgrading and modernizing the stockpile. In the weapons science, there's really no plan currently. It's sort of, we might get to looking at upgrading some of these things in the 2030s, 50s timeframe, whereas China is, iterating on their plan very quickly. And so, the time is really now, from my perspective, looking at China's schedule and their clock. They are on a really fast mission, moving very quick. And if we don't fill this gap, we'll have a whole new stockpile, but then China may have far more sophisticated new weapons that they will be fielding that'll pose new capability problems for us.
One of the things that I was noting too, it is noteworthy. It's $10 million, which doesn't seem like a lot, but it is important given the timing of it, which tells me that Congress understands that, first of all, it's reacting. It seems to be reacting to what China's already doing. So I deal with people who sort of accuse the U.S. government now of engaging in something of an arms race with our delivery systems, nuclear delivery systems, or with the enterprise. It's like, well, no. The Chinese are moving so fast. The Russians have already finished modernizing their nuclear weapons program, and now we're living in a post-New START environment with facing down two nuclear peers. We have to adapt not only our delivery systems but the enterprise. And the Strategic Posture Commission concluded that the program of record is necessary but not sufficient. And so we're going to have to do some things, again, because we're trying to deter these two peers that are increasingly collaborating. The other thing I think is important is, Keith, just sticking with you for just one more minute, so we have the Congress paying attention to this, but also since 2022 there have been, you note here, a half a dozen inertial fusion companies that have raised in aggregate well over $1 billion. Mm-hmm. I like that number better, in private capital to commercialize approaches to fusion. And so that seems like a promising.
Yeah, the important thing we talk about increasing interactions right now to win this race in fusion. We're not talking about launching programs in all different directions. We're talking about looking at milestone-based programs and working with industry that has raised significant capital already. What milestone-based program means that the government gets something out of the investment it makes and it doesn't overcommit. And you have to have a scale appropriate enough to actually advance capability. So Pacific Fusion, we found in 2023, we've raised a little over $1 billion toward building our commercial energy mission, with an engagement today in a milestone-based program similar to NASACOTS. We can align the requirements and needs of what NNSA has to build into that facility out of the gate. And so yes, there's significant private investment on that the government gets to leverage. 2026, I think, is a defining year. We're looking at China building things by the end of the decade. This year, this cycle, the 2027 cycle is about to start, is the year that we must align on this if we're gonna win.
Decisive. Yeah. Daniel, you had made some notes here about potential opportunities to promote national security jointly between private fusion and NNSA laboratories, and you had kind of listed what some of those things are. Do you want to kind of get us started there to think about how we might do this?
Yeah, I think there's tremendous opportunity. I think Jimmy said this earlier, right? There is no NNSA plan to build any major science capabilities in inertial fusion beyond upgrading the existing ones in the next decade. I contrast that with my colleague here. Pacific Fusion is hoping to build a pulse power machine that would be more capable, I think, than any of the NNSA facilities potentially by the end of this decade. So big potential for collaboration. Again, the NNSA needs to decide exactly how they would like to do the collaboration with the private sector. But even if it was limited to we watch and observe and they build this thing, it works, and then we buy a copy or we rent it or lease it from them after they're done with it and move on to a high rep rate facility. There's many options. But fundamentally, they're going to de-risk a lot of the technology. They're going to de-risk the risk of maybe we build it and it doesn't work and all that stuff. And they're going to do it on a time scale that's really going to accelerate the national security side of things. So I think there's lots of upside there. The other thing that's going to happen, you've alluded to it in your opening remarks, is the supply chain. Mm-hmm. So for a fusion energy economy, there's a tremendous amount of things that are going to have to change in the country to supply the tritium, to supply capacitors, like lots of, I'll call it boring stuff that's not super high technology, but we do not make any of it in the quantities that we would need. Even to build the Pacific Fusion device that's being proposed is going to take a major transformation of our national industry. And I think this is good. It will also then benefit the NNSA if it's a fast follower, so to speak. The NNSA can come in and the private sector will have developed the supply chain already, and we can come in and maybe do things more cheaply than we would have if we were leading. Part of the reason that the government and NASA and all these federal initiatives are often expensive is because we tend to do things first. And doing things first means there is no supply chain, you don't quite know how to do it. And the opportunity here is I hope all the best for the private sector, but some of them will fail. And so then the federal government can be learning from the failures and not repeating those and repeating the things that are successful, which is functionally what China has done to us, right? So this is not a mistake that China is building all these things. They've been working on this for more than a decade. I went to conferences in the early 2010s, where they had just built their copy of the Z machine, and their scientists were frantically copying and pasting everything we did on the Z machine at Sandia or the Saturn facility at Sandia, and demonstrating to their government that they could do those things in order to convince their government that they were ready to take that step. The success of ignition on NIF made that a lot easier for them. The government, we de-risked all the technology for China, which allowed them to take that bold step forward. And in a sense, that's the opportunity we have with the private sector, is let them help us de-risk a lot of the technologies so that we can take more aggressive steps on the federal government side.
And I know the next panel will talk about supply chain, and there's been a lot of good work, like from SCSP, people like Abby Remla and others I think are in the room, to look at some of this. But we don't want to end up, where Pacific Fusion or other companies are buying their capacitors from China. But that's the risk that we could be in. Is right now for AI, a lot of the stuff that's building in our data centers is coming in from China. We don't want to be there, particularly in the nuclear weapons space, and have any of those dependencies.
No, and again, that was something else that we concluded when the Posture Commission was looking at this, is if the United States wants to go fast, but before we can go fast, we have to have the supply chains that give us the ability, and the workforce that gives us the ability, so that if the president does have to make a decision, there's some decisions that are facing the country that are going to have to happen at the presidential level. But we Americans who are working on this in the national security apparatus, the labs and private sector, want to optimize the president's options so that he can decide what he wants to do, not limit them. But that means there's a lot of work that has to be done on the front end to make sure that we have the ability to do this. I think about that with some of the other delivery systems. Even if we wanted to produce more quickly, we couldn't, which is why we need to be working to make sure the president has those options. I want to, Daniel, you mentioned faster, so the collaboration can lead us to faster technology, improved supply chain development, workforce, growing the workforce, which is going to take time. So that was another one. And then de-risking, you mentioned that. Okay, I think you covered all of those things. If you wouldn't mind, what are some of the risks that are still there, though, that you're kind of tracking and that you just want to put guardrails on so we're thinking about them now?
Yeah, so workforce is like a double-edged sword. One of the cool things is, like, the year after NIF got ignition, went to the conferences, and every professor I spoke with said the number of students that wanted to work in their groups had more than doubled overnight. And so the cool thing about the investment in the private sector in fusion energy is, over time, it's going to grow our scientific and expertise, scientific and engineering workforce, and that's going to be good for everybody in the field. In the short term, there has been a lot of people leaving the national labs to go work for private fusion energy, or to co-work in some cases for private fusion and the national labs. And so we're a little bit worried about brain drain. I'm not that worried in the long term. I think this is it's a healthy direction for the country, and a rising tide lifts all boats, so to speak. I mentioned earlier about the technology. So one of the key things that I'm particularly concerned about is the computational modeling tools. Those are, in a sense, we spend billions of dollars developing those tools, perfecting those tools on our facilities, and we use those tools to study phenomena that are very directly relevant to defense. And so at a minimum, all the tools we develop at the national labs are export controlled. Many are classified, and we don't share them, obviously, with other countries. So I think for the fusion companies to make progress, at some level, they would benefit from having access to these tools, but we need to figure out a way to do that that doesn't also proliferate the tools beyond the control of the government. So that's sort of an obvious concern. I think it's manageable, but let's just say the policy is not quite settled on how best to approach that.
I mean, one thing I'll add there is I think the idea of industry working hand in hand with government on defense applications is not new. There's a pretty large Department of War that executes a significant fraction of its mission exactly that way. So I do think that these are the kinds of things that are structural and solvable, but it comes back to the government deciding it wants to do something, laying out a plan, and then go ahead and taking a step to do it. And we're at that moment where we need to do that.
Yeah. Yeah, it'd be good to do this in the next year. Like, he'll have built the facility before the government would make a decision if we take too long, right?
That is a great place, I think, to take a pause, unless, Jimmy, you wanted to have something burning that you want to say. Okay. Questions from the audience. If you could please raise your hand, we'll have a microphone brought to you. If you could state your name and affiliation, and then a brief question.
This is great. There's nothing controversial in fusion.
Nothing about China's nuclear program. Oh, we do. We'll go here in the front.
Hey, thank you so much. I'm John Corrigan from Silverado Policy Accelerator. I don't want to jump ahead to the next panel on supply chains too much, but points from both Jimmy and Dan sort of lead to this question. Setting aside the science at the bleeding edge and assuming success, both in the US and China, is there a scenario where China essentially ups its export control regime to account for hardware around scaling and deployment that negates any US win, so to speak, in the bleeding edge science space? Because I would think that there'd be a very clear connection for Beijing between exports of hardware and its own national security concerns. Thanks.
I mean, obviously, they're going to want to try and secure the same codes that Dan and his colleagues have been developing, and those are, strictly controlled within China, for military usage. On the supply chain, that's an interesting question. There are, AI and semiconductors is a good parallel where the U.S. has imposed a large number of controls on China to impede its semiconductor development. China obviously has retaliated with its rare earth restrictions, but there's many other tools that they could retaliate. There's many other parts of our AI supply chain that, I don't want to go into all the details, but they could squeeze if they chose to. But I think they know the U.S. has also other things that they could then. And it's a bit of like mutually assured destruction where, if you go down that route, the U.S. then imposes more, China imposes more. And so, I don't think we're always going to be at this equilibrium, perhaps, but I do think China is worried about if they go too far, we can always counter-retaliate the United States. We do have still a lot of leverage that can be used. I mean, even though China has made a lot of efforts in localizing their supply chain, there's still many things, for example, high purity glass that they are importing. Some of the really important scientific instruments for metrology and inspection are coming from Germany, Austria, the United States. China will work to replace those too, but China can't replace everything overnight. And they want to be part of the global scientific enterprise. I mean, Chinese scientists are working with European, Japanese, Singaporean, less so the United States, but more with Europe very intensively, and they don't want to be caught having these restrictions impede some of that collaboration that's important to them.
Dan, did you want to add?
Yeah, I would say we've already been experiencing this, at least in the defense side of things, where we've had import-export controls for decades on a lot of high-energy laser technologies, and there's been import-export controls related to specialized capacitors that both pulse power machines and lasers use. And the result is that China built up their own indigenous capability, and the danger is they've been actively building over the last 15 years, and our construction has diminished. So in some sense, they already have more capability than we do today. I'm not that worried about it because all the private fusion companies, like my colleague to my right, are actively talking to the supply chain suppliers and are working on strategies to build it out. I think it's this, to do this even up to the full scale of a fusion economy, I think is well within the capacity of the United States to achieve.
Well, Jimmy, your answer, though, also made me think that it seems like we should be mapping this out with allies and pulling in the same direction.
Yeah, I mean, it's very well known that the United States over the last 8 years has put a huge focus on the topic of research security, ensuring that the proper vetting is done on the researchers that come work at our national labs and our universities on sensitive dual-use military research. While we've done a lot of good work, I'd say Europe and Japan, Singapore, South Korea, some of the other industrialized nations, Israel, are not up to the level that we are.
In their collaboration
with China. They have not imposed similar type of vetting and security and risk management procedures that we have. And so there's a lot of work that I think that, for example, our State Department, people like Undersecretary Donato can work on is, and people like Michael Kratsios, I know this is a focus area for them, is working with our allies to get them to improve the security of their own research infrastructure. Otherwise, you'll have Chinese nuclear weapons physicists, for example, Stanford, the publication there was showing how the Chinese Academy of Engineering Physics, their weapons scientists were using Stanford facilities, collaborating with them on demolition simulations. That type of collaboration we should be better at in terms of understanding, hey, this one doesn't make sense. This is obviously for military end use. And so applying those standards here to our allies also should be a very important priority.
That's great. Question here? No, she's coming. Yeah, thank you.
Thank you so much. Jane Nakano with CSIS. Just to build off of what the conversation you two just had. So beyond more of a researcher in security, clearance and what have you, what's the status of sort of export control coordination? Because we've seen over the chips, Washington, we tried to work with the Japanese and Dutch, and I'm not an expert in that field, but just curious, what have been some of the lessons that we're trying to draw from our past experience and be able to proactively have more of an allied partnership to address some of the tech transfer and export control vis-a-vis China? Or, yeah, thanks.
Good question. Anything more?
Maybe I could just add, I think to Dan's point, once we control things for legitimate reasons, national security, we have to ensure that we're investing in our domestic capability. It's a perfect example here where we, restricted, rightly so, the high purity glasses and lasers that are important for laser inertial confinement fusion. But then if we don't, for example, have a large facility like NIF to create that supply chain, we wouldn't have a domestic capability. So it's for example, in these areas, we'd be thinking about investments in those important components and technologies domestically and with our allies so that we don't let it languish. And the demand needs to be there.
So what about, it's curious to me though, if China's collaborating with these other countries that are close allies with the United States, is there anything that the United States is not exploiting with our allies? So if we could box China out and convince them not to have China in their labs, but they are more advanced in some area than we are, and if we could take advantage of this ally expertise in this one particular area in which is there anything like that comes to mind that we're not thinking of? Because it's curious to me, some of those, Germany, Israel, that's where the Chinese are clearly seeing something that benefits them. Are we missing something?
I think one curiosity I've had is in defense space, we have collaborations, and specifically in the inertial confinement fusion program with both the United Kingdom and with France. And in fact, France has a near knockoff copy of our national fusion facility that they deliberately, as a strategy, were a fast follower. They let us lead on all the technology, and then they copied a lot of the key pieces of the technology and built their own for their own nuclear security enterprise. And yet, in the fusion energy enterprise, the United Kingdom is right behind the United States, I think, in terms of number of fusion energy companies. And yet, there's relatively minimal attempts to collaborate in the fusion energy sector. And I'm not as deeply familiar with the French fusion industry, but it does seem like there could be an opportunity on the private side to be doing more. And that has been a successful strategy on the defense side. Why not explore that as well? With, of course, I'm also the one saying, hey, we got to worry about proliferation concerns. But again, I think it's manageable.
One thing to note as well, so there's heavy Chinese-Russian collaboration in this space. So Russia has a similar program. It's older and a little bit more outdated than what China has, but there's a lot of collaboration. A lot of Chinese researchers spend time on the Russian machines, and we don't know, but it could be possible that Russia will also send its scientists to work. And we have to think about then, if China provides Russia the access to these state-of-the-art new physics labs that are modeling weapons, what we have to think about then, well, what new capabilities would that give Russia as well? So that's a bit of a eerie prospect. But it's not, given the state of the Sino-Russian relations, it's not out of the realm of impossibility.
I think that's so important to foot stomp, because there was a lot of skepticism in the expert community even just 6-7 years ago about this kind of China-Russia collaboration. I mean, anytime you'd have somebody sort of imply, well, China might be behind on the nuclear front, but if Russia helps them in these ways, they might go faster. And then you would immediately have people say, but they have such distrust. Oh yes, there's this no limit partnership, but there are very serious limits. And we've actually seen, I think it was during the first Trump administration, it was confirmed in an open hearing that yes, we do see the Russians collaborating with the Chinese in areas that could advance China's nuclear program.
Yeah, I think there sometimes is a desire to look at what others are doing and sort of try to explain to ourselves that it's not really what we're seeing, especially if it challenges the idea that we're not in the lead of a certain technology, especially when we invent. Fusion is exactly at that intersection, and we're at a moment in time, and this year is that moment, where if we don't bring together industry and government to both address the enormous energy challenges and national security challenges that fusion can offer, we really will sort of skip off the atmosphere of staying ahead in this area. And and we've heard today from different perspectives on the panel that it is a mature industry. It is something that's industry. It is a mature field. It is something that industry is pushing out on. And what we're lacking is that top-down drive from the government side to make sure that we stay ahead. While companies like Pacific Fusion are investing in certain elements of the supply chain, it's not realistic to sort of say, well, industry, figure all this supply chain stuff out, onshore everything that you can all by yourself. It really has to be a coordinated effort, and that's something only the government's positioned to do.
Great. We have time, Nadia, for 6 more minutes? Okay, perfect. Okay, question over here, and then we'll go here. Why don't we bundle them? We'll have you ask your question, you can ask your question, and then we'll...
Francisco Marcos from Greenmantle. So for the last 2 years, if you go to any fusion panel, it seems like it's very clear that if we want to take this competition seriously, more government funding is needed. And I'm curious, what has been the most specific pushback that you've heard from policymakers? Because I found that the arguments are very compelling, but I'm sure there's some very specific pushbacks. And what have you found more effective at addressing those concerns?
Great. And then question over here. I'm going to give you a minute to think about it.
Okay.
And then we'll have him ask his, and then you can...
Hey, Ryan Alimento with the Breakthrough Institute. Kind of building off of that, I'm curious how well you all feel that the national security agenda actually aligns or maps on well with the various approaches and technologies being pursued by all of the American fusion companies. There is, of course, limited capacity for the government to match the private sector in the amount of capital that's being allocated to all of these companies. And obviously, one of the critiques of the Milestone program is that there isn't enough funding, or it's being distributed between too many people. That there are too many cooks in the kitchen, so to say. I'm curious, especially with the interest in ICF and the priorities of the NSA, how well does that line up with anything like MCF or a hybrid approach? And what are the limitations of the government's defense priorities in providing capital, providing resources for private fusion, which is aimed at commercializing and serving the power sector?
Good questions. Yep, you can take a bite at either one of them.
Give some brief reflections. I think this administration has done an outstanding job sort of aligning industry and government interests in fusion, both for energy and defense. Much more progress in the last 6 months, even less actually, last 3 or 4 months on this front than the previous few years, I would say. And so that alignment takes a little bit of time. When you take a government, having run the fusion program for NSA for a number of years, when you have to kind of decide where you want to win and where you can win and invest there, and what is the impacts of those investments. You have to make those decisions, and that takes time to sort of figure out. But I do see a lot of forward progress right now. This last year's been about planning. This year's got to be about execution, actually aligning the resources across the administration, Congress, and that industry and the national laboratories, another incredibly important element of this whole conversation. So lots of forward progress, not there yet. On the other question, they're sort of different arms of the DOE that care about these different things, right? There's the Office of Fusion Energy Sciences or Office of Fusion in the Department of Energy, and NSA, being a subpart of the DOE, cares more about the defense angle. So they have sort of different elements that they look at. It is why it does take that sort of, again, a holistic thing, connecting the White House to the agency with a combined strategy of how to address the many challenges that this moment in time can't actually address. So it's not pick this company, pick that company. It's having a holistic strategy, but then executing on it.
Yeah, and I'll just weigh in terms of the challenges. That someone mentioned it earlier. The biggest challenge we have is we, as a country, didn't invest in our stockpile, and so we're in the midst of tens of hundreds of billions of dollars investment in the nuclear stockpile modernization, which is everything from the things that the NNSA supports on the warhead side, all the way to the Minuteman silos and you name it. And so a tremendous amount of money being spent there. The emphasis within the NNSA is on production, and Congress is very concerned about not taking money away from those priorities and deflecting it toward what they see as fusion energy, not their mission. So I think it's going to require collaboration with the NNSA, but the leadership is probably going to have to come from the DOE side to help facilitate this partnership. And I would like to see more collaboration and conversation between the DOE side and the NNSA side in that space. That would be necessary to overcome the challenges. I'm a big fan of the milestone-based approaches that were mentioned earlier. It's a way to make the money go farther and to not overcommit the government funding. In other words, you make the companies deliver and put their money where their mouth is and show that they can do something that the government is interested in before you give them money. That was the nature of the COTS program that was alluded to earlier in the space domain. Worked very successfully. I think a partnership model like that could work here and make whatever limited resources we can devote to this go that much farther.
And I think just to add on that, it's also emphasizing, that this is not just happening in a silo here, that, we have to understand and assess the capabilities that China's bringing online and what they're going to mean for our national security. I don't think we even know the real answer of if, China has all these new ICF fusion facilities for weapons effects testing, what new capabilities will it give them? What kind of strategic national security problems will that present the United States? I think if we answer those questions, they will not be very positive for the United States, and that also could help motivate policymakers to understand that this portion of fusion has a direct national security relevance, and that connection I don't think is recognized widely by enough members of Congress.
Well, that is why we're having this conversation today, and I want to thank all of you for your years and years of dedication and study and expertise that will benefit our country and our allies. And thank you so much for sharing it with us today. Please join me in thanking our guests.
We are going to touch on, do a deeper dive, and the first panel sort of hinted at supply chain issues, but the purpose of this panel is to really do a deep dive, to come away with an understanding of what those vulnerabilities and challenges are, but also I'd like to get into some specifics about specific tools the U.S. government could use to address them. And I have a great panel here I'm excited about this morning. I have to my left Caleb Barnes. He's an Associate Director for Fusion at the Special Competitive Studies Project. I urge all of you to look at their October 2025 report, the Fusion Commission report, and then subsequently Caleb did a really interesting study specifically on the supply chain issues. Oh, great. And he happens to have a Master of Engineering in Nuclear Engineering, so I didn't know that. To his left, Jackie Siebens. Jackie's currently the Vice President of Public Affairs at Helion Energy. Helion's based in Everett, Washington, and it uses pulsed magneto-inertial fusion to achieve fusion. It's a different concept than that used by the National Ignition Facility, and I think that's important and relevant because I think in what I've learned about this space is there are different approaches to getting to fusion and the implications of that for supply chain, and I think that will be important to draw out. Then we have Sean Walsh. Sean is the Chief Marketing Officer for Peak Nano, a nanotechnology company, but he has done a lot of deep dives into the energy grid and into the fusion industry, and he publishes something he's a contributing editor to the Fusion Report, which I'm new to, so I will now subscribe to the Fusion Report. And he has deep expertise in these supply chain issues. And last but not least, we have Trent Bauserman. He's the head of federal affairs for Commonwealth Fusion Systems. Commonwealth came up at the earlier panel. It's a Massachusetts-based company, and it's using a different approach to fusion, magnetic confinement approach, also known as a tokamak. And prior to that, he served on the Hill in a key position for the former majority leader, and he served for 5 years in the Obama White House as a special assistant to the president. So we have a great panel. I would like to jump in now and sort of ask each of the panelists to address what is the problem, what's the relationship between what's happening at these fusion companies, the innovation going on there, and the supply chain, and the idea of commercialization of fusion. So how would you describe that? I'm actually going to start with Jackie.
Okay, thank you. Thank you for having this conversation. And I just loved how in the previous panel, you could tell that we just couldn't help but try to like jump ahead to this very hot, important topic. So I'll just want to start by saying that we are at a very similar moment. And in the previous panel, we heard about the fact that we had this moment in the space industry where it was sort of like a do or die. Like, are we actually going to have the government partnerships with the private sector to really, horrible pun coming, rocket this into the future in a way that's really going to set the U.S. up for leadership? And I think that we do find ourselves in a very similar moment with fusion at a time when AI is emerging as well. And this is really going to set the tone and set the metrics for global leadership for the next century and beyond. The fact that we have AI emerging at the same time as we finally have we're on the cusp of commercial fusion is an enormous opportunity that we're at great risk of failing to actually capture the leadership at this key moment. And one of the greatest ways that we are on the fringes of failure is directly related to supply chain leadership. What do I mean by that? So at Helion Energy, you talked a little bit about our approach to fusion. I'm not going to go too far into the technical weeds here, but one of the most important components in our machines are high voltage electrical capacitors. These are things that are used not just in fusion. I mean, this is a widely used component across the electricity sector and beyond. And for our purposes, for our machine, we use thousands of these in large banks for our commercial systems and for our pre-production system right now. And we found ourselves in a situation where we were painfully dependent on China for this technology and for these components. And we actually went around and we talked to suppliers that make capacitors here in the United States. But unsurprisingly to most people in this room, it was very difficult to get companies interested in scaling up production of this component that we needed, only us at the time, when we don't have a rapidly growing commercial space yet, right? We're in that really awkward moment that technologies find themselves in. But we found ourselves, we were very, in a very great position with our investors, that we were able to start building out our own manufacturing capacity of our own capacitors. So we're vertically integrating that and scaling that up because it is so important to our machines. And because the mission of our company is not to just build one fusion plant, right? We have a public power purchase agreement with Microsoft to deliver the first commercial plant. It's 50 megawatts in 2028, first electricity in 2028. And we're very excited about that, and we're on track for that. But the mission of the company is to build hundreds of these, thousands of these, deploy these across the world to meet the energy demand. The only way that we're going to be able to do that is if we have the supply chain in place for us to build these as rapidly as we know that we can. And so getting back to the supply chain, we've taken the sort of aggressive and difficult step to vertically integrate. We're now, for our pre-production machine, which we're operating now, we actually manufactured around 15% of the capacitors that we needed for that machine. We are scaling that up rapidly, just built a new facility. And so that's one solution to this problem, where we're dependent on China for a lot of these components. But when you really get down to what is the dynamic vis-a-vis US-China when it comes to a myriad of components across the supply chain, it's not just the fact that they are in a much better position already with built-out large-scale manufacturing and low cost. It's also the fact that the quality is better. There are vendors here in the US for small precision metallized components that we need on our machines. We need hundreds of different small components. And we can go buy them here in the US for $50 a piece. And it's hit or miss quality, where in some instances we're going to recycle up to 30% of the product we get from US vendors. Or we can go to China and buy them for $7 a piece, and it's precision quality every time. And so getting to your question, I know we're going to get into this more, what is the path forward for the federal government? What's the role of the federal government right now?
I'm going to hold off on that because I want
Yeah,
to comment
sure.
on the
Go for it.
description of the supply chain
Yeah.
problem. So
Yep.
Trent, you're working for a different company using a different type of fusion. A couple things. Jackie alluded to the sort of chicken and egg problem of can you explain that? You've spoken about that too. And then is Jackie's description of the supply chain problem set similar for a company like yours?
Yeah, so again, thank you to the Hudson Institute for inviting me. As the fusion industry supply chain report notes, as well as the SCSP supply chain work that Caleb helped spearhead, we think this is really a chicken or egg issue. The biggest question our vendors...
What do you mean by that? Yeah.
Yeah, right. So CFS, founded in 2018, $3 billion company, over 1,000 employees. We're building Spark just outside of Boston. Spark is procured. Spark is 80% complete. But we're already starting to think about the commercial product, ARC, which we announced we're going to build just outside of Richmond, Virginia, breaking ground on that in a few years, first power on the grid, early 2030s. The biggest question from our suppliers and vendors are you going to be a company? Are you going to be an industry? Can you make a pay order today? Can we sign a deal today to start selling you X widgets? And I think that is a thing that most fusion companies are facing right now, which is nobody has done the thing yet, right? We haven't produced fusion power on a commercial scale. That's what we're all aiming to do on very aggressive timelines. Once we do that, I'm sure that we will have new resources as an industry to start investing in that type of procurement. But from our perspective, it's a couple of things. One, it's not monolithic across various technologies. So companies that are pursuing inertial confinement need lasers, which mean they need a special set of technology. Magnetic confinement, we don't need that. We need a lot of HTS tape. So a good example for us, Jackie's anecdote is electrical capacitors. For us, it's HTS tape. When we founded the company, there was a real question as to whether or not there was enough HTS in the world to even make a single magnet out of it, right? We have now, 95% of all the world's HTS tape now is in Devens, Massachusetts. We have scaled that supply chain. But will it be there for ARC scale magnets? And to Jackie's point, we are all thinking about rapid scaling. So it's not just for us, ARC 1, it's ARC 5, it's ARC 10, it's ARC 100. And so the real question for us is, will those vendors be there? Is that supply chain secure? From an HTS perspective, there are several companies in the US that are aiming to develop a US supply chain for HTS, but it's not really there. And what we are seeing, and Caleb can talk about this more, is China is taking it and going by orders of magnitude. They aim to own the supply chain. And so that we're in this odd moment of it is a chicken or egg problem for our vendors and suppliers. They need to know that the customers are there. But it also requires they have to grow at the same time we're growing. And so we're kind of tackling this at the same time.
So now I'm going to turn to Caleb. So how would you summarize what's in that 40-page report, and are Jackie and Trent accurate? And then last but not least, Sean, your comments on this issue of these vulnerabilities and how you'd characterize them.
Yeah, so certainly accurate so far. One of the things that we did in this report, in addition to the details, is we charted out every company, and then in a graphic here, we did every company that's either in the milestone program or the valuation of funds raised over $50 million. And then by approach, and then what components they might use. And so if you want to get an instinctive look at what type of fusion approach will use what devices, what materials, this is a good starting point. I think in the course of this talk, we'll probably spend a lot of time on details of what the challenges are and the potential solutions for them. But I want to just take a second to reframe and note that fusion on the whole could be something that overall liberates us from a lot of supply chains rather than confines us to them. There are certainly opportunities for certain companies, but on the whole, when you run a coal plant, when you run a natural gas plant, you don't get more coal by running it. When you do fusion, you can get more tritium out than you put in. It gives you its own fuel. That's an incredible incredible opportunity for the most energy-dense fuel source that we know.
Yeah, and Sean, and then I'm going to go to Jackie quickly because I know, Jackie, you spent a lot of time thinking about the opportunities of this fusion economy and what we can achieve. Sean?
Yeah, I'd like to kind of do two levels to that answer. If you look at what has happened with solar panels, batteries, take your pick, okay? Again, the US has developed the landmark technology. The question is, are we going to hand it to the rest of the world? Most dangerously, are we going to enable China? I can tell you as one of the suppliers to these companies that you cannot make these materials in China without giving them the secrets. There's no way to tell them, I need a nanolayer precise capacitor film without telling them how the secret sauce is made. So we have to make the fundamental strategic decision not to repeat the errors of the past. The second part is when we think about the supply chain at a macro level, if fusion has the success that we all anticipate, whoever owns the manufacturing of those parts, the supply chain, what goes into it, they dominate a multi-trillion-dollar industry and they drive how the supply chain behavior across the globe works. And then the third part I'll give you is that we as a manufacturer of dielectric capacitor film, right now, ironically, our number one problem is getting enough power so we can build a factory in the United States to build power. The machines that we have to procure outside of the few manufacturers in China, there are no machines we can buy in the United States to manufacture dielectric capacitor film. And it's about a 3-year lead time. Now, the good news is we still have time to get this right. This is not lost yet. But if we do not enable things far more quickly, so if you look at what Secretary Wright has proposed since he took over the DOE, the fusion roadmap, the quantum roadmap, the AI roadmap, all of these things are tied together. They're all intimately used to solve the same problem. And if we fund those properly, and in turn, look at legislation that's in there like the Fusion Manufacturing Parity Act, those are the steps we have to take now. The game isn't over yet, but it is, again, purely one of those games that it's ours to lose.
So are these roadmaps, I'll ask each of you this, starting with Jackie, are these roadmaps enough to, what's the next level of what are the top 3 to 5 things that the government, meaning Congress and the executive branch, really could do today over the next year, 2 years, 5 years? What are sort of your top 3, Jackie, or top 5?
Yeah.
And then if there's agreement, that's actually a good thing, right? I mean, then we'll get a sense, but there might not be.
I mean, I think at the absolute highest level, it's a genuine paradigm shift from how our federal government operates. We have to move from operating in a recovery strategy, which is what I would describe CHIPS and the Inflation Reduction Act as. Those bills, those policies are not first mover policies. Those are, we screwed up, and now we have to try to recover from that and like somehow reshore like things that we lost that we never should have lost in the first place, right? And so that's the overarching framing I want everybody to take away from this, is that this is our moment with fusion and AI to stop like getting ourselves in these situations where we're having to pass these enormous bills to recover things that we never should have lost in the first place. I
love that frame, by the way.
And so, thank you. And so how do we do that? What does that actually look like? Well, thankfully we have, well, maybe not thankfully, but we certainly have some hard lessons we can look back to. And I think you mentioned batteries. So if we look at lithium-ion batteries, this is my favorite thing right now. I've gone down, like the thing I never thought I would learn about in the fusion space so deeply is lithium-ion batteries. But this is, to me, the best analog for us to think about right now, especially in the national security space. Because what I've learned is that this is something that, to be quite frank, people have their hair on fire about right now, because we're in the very situation with lithium-ion batteries that we don't want to end up in fusion, where that supply chain is so dependent on China. And it is a true national security risk in our defense apparatus, because we're using those batteries not just for EVs, but in drones and across our national security and defense complex. Now, what does it look like? And I'm going to say this as quick as I can. What are the things we can do right now? You mentioned the bill to expand the 45X manufacturing tax credit to fusion components. That's a huge and important first step. That's the kind of thinking that we need policymakers in this administration to be doing in this moment. I think that what we need to see happen is there's a parallel track here. There's a lot of conversations, and this is included in the SCSP report, and it's focused on Department of Energy, and that's important, and that's where any focus of government funding or effort has always resided, has been in the Department of Energy. For fusion. And that's because up until very recently, this has been a largely academic exercise, R&D focused exercise. But we are transitioning in this moment in real time to commercialization. We have to start waking up other pieces of our government to act in this time, and that includes Department of Commerce. And so this is one that I really think that we need to look hard at and say, how do we do something that is a first mover initiative? Not a recovery initiative like CHIPS, but how do we get commerce activated to get ourselves in a position where we're winning out of the gate instead of 15 years from now, all of us are sitting in hearing after hearing in the Senate about how do we reshore the fusion supply chain. That's the nightmare we have to avoid.
Yeah.
And Sean, do you agree that it's primarily within commerce that this is going to happen? Is it broader? Is there a broader interagency play here? And the other, I'll ask the other panelists too.
It is, in some ways, one of the most profound gaps we have. And let me go through this in a couple of scenarios. There was two articles recently put out. There were interviews with Jensen Huang from NVIDIA. Here is the person who owns every AI chip on the planet. He has 3 data centers in Santa Clara. He can't start because he doesn't have power. Satya Nadella, the CEO of Microsoft, said, I have 50,000 NVIDIA GPUs sitting in a warehouse. I have the data center built, but I can't turn them on because I don't have power. So we think about where fusion fits strategically. If we do not fix the power problem, we will lose AI. Again, a quote from Jensen Huang. China's not going to beat us because they don't have the chips. They're going to beat us because they have more power and they can throw a lot more inferior chips at it but solve the same problem. So if we want to grow our economy in every aspect, if you don't have power, you don't have an economy, and that's why it's got to be out of the DOE. It has to be broader than one agency. It has to be commerce. It has to be everything that we consider fundamental to the growth of the US economy. Because you want to reshore things, try to reshore all those factories in Japan and get power. Our chief operating officer was the head of operations of the supply chain for Apple for a number of years, worked directly for Tim Cook. Couldn't do it if he wanted to today. And it all boils down to one fundamental thing. We don't have power. And that's why this is so critical.
That's sort of the chicken and egg, Trent, in a way. We need fusion for the power.
Exactly. You know, it's interesting, right? Because AI and fusion are kind of coming right at the same time.
Yep.
You know, which is AI is benefiting from years of investment. It is more, you know, there's less technological risk associated with AI than, say, fusion. AI now needs more power than exists, right? And we're seeing huge demands not only here in the United States, but around the world. AI also helps enable fusion. And so you get into this virtuous sort of feedback loop of one supporting the other in a symbiotic relationship. I want to touch on something Jackie said, which is we are asking Washington to do something that they're not accustomed to doing, which is Washington very much focuses on 2-year, 4-year, and maybe 6-year cycles. And fusion is right on the outer edge of that. And so right now, you know, if you pick up any paper, affordability is dominating the political narrative, and justifiably so. But fusion is unlike any other technology. It is a civilization-defining technology in the way that the steam engine was, in the way that the internet was. And it is no longer a question of if or when, it is a question of where. And the risks of this country, to this country, of seeing fusion deploy and scale outside the boundaries of this country present huge risks. And so to Jackie's point, I would agree with everything that she's saying about 45X. We're big proponents of that tax credit. Very interested in what commerce and other departments could be doing. But also, we need an industry. And so a big thing CFS and some other fusion companies are pursuing is a demonstration phase of the milestone program, which is similar to what we've done with other innovative new technologies that we're trying to bring to market, where we're trying to get through the valley of death, bring in capital, get through the risk challenges, and deploy the first fusion power plants. And so I think if you think about it holistically, we need a milestone program at scale, which is helping to cost share some of the first fusion power plants, while at the same time we're developing the supply chain here concurrently, because that's what our competitors are doing. Then that looks like a cohesive policy that this country needs to undertake. And the last thing I will say is, I don't think most policymakers in Washington understand just how close this technology is. And all of us in the fusion industry are used to the jokes of, give us a dime, we'd be very wealthy people from all the fusion jokes. But I think this is a technology that is tantalizingly close to commercialization. And I think we in the fusion industry kind of take that for granted because we have this knowledge. Most policymakers are not tracking that. And so this is much more of a nearer term solution to our energy challenges than gas turbines and advanced fission. And we ought to be thinking about fusion as part of a broader portfolio of meeting more near and midterm energy solutions than being this decades away, always has been, always will be, but if it was around, wouldn't it be great? And it's like those stakes have changed fundamentally and just in the last few years.
Caleb, and then just to warn the panelists, I'd like to go, I'm really surprised I haven't heard the term regulation. I'd like to get to that too in terms of what the government can or shouldn't do. Caleb?
Sure, so a list of 3 to 5 things, I'll give you 4. So number 1, tax credits. Top recommendation in the supply chain report, already mentioned multiple times on this panel. It's proven, it works, and the cost to the government is not actually spending money, but just opportunity cost of money that it could have.
And that's the 45X?
Yep, 45X.
The main one, okay.
Yes. Another option could be ensuring availability of raw materials that some fusion companies are going to meet. So that could be lithium-6, it could be beryllium, it could be rare earths for laser diodes, it could be deuterium. So there are a couple of raw materials that are niche enough that there is not that much of a supply for that we need to make sure we have some access to. And then we have a couple recommendations from our commission report, which was co-chaired by 2 sitting U.S. senators and then had a lot of representatives, including the CEOs of both Helion and CFS. And those include elevating fusion to a national security priority, which would just makes everything go a lot smoother in Washington. Once you have that sort of elevation, it is much, much easier to get things through that you need. And then another one is about $10 billion in funding. And so this would include a demonstration element of milestone, as Trent mentioned. It would also include a couple of facilities that would be really, really helpful for the industry. That would be public facilities that would give us scientific knowledge. Sean mentioned how China's been able to build out a lot of energy infrastructure or with batteries. Last year, China installed over 500 gigawatts. 500 gigawatts, that's about a third of the US grid. In nameplate capacity. Most of that was solar panels. Now, if we can do that kind of thing with fusion, we get something much, much better, something that gives us that amount of power, and it gives us that power when we need it rather than when it's available.
Yeah. So Trent, regulatory, how much, it seems to me that this is actually a great opportunity with this administration and its focus on regulatory to make huge inroads over the next couple of years on this. How important is that to commercialization, to the supply chain scale?
Yeah, so excellent question. I don't think there's an industry in Washington that wouldn't say, we would love to have more certainty and we would love to build things faster. The exciting thing about fusion is the big critical risk for our industry several years ago was we might be licensed like a fission facility. And thankfully, after several years of study, the Nuclear Regulatory Commission voted unanimously in 2023 to license us as a particle accelerator. What does that mean? It means that for CFS, our facility just outside of Boston is licensed by the Commonwealth of Massachusetts. Our power plant in Virginia will be licensed by the Commonwealth of Virginia. We can get those licenses in a matter of a year or two and a few $1 million versus perhaps a decade, perhaps $500 million for fission. And thankfully, Congress came along in the ADVANCE Act and codified that. So from a nuclear licensing perspective, we feel like we have the certainty we need to make significant billion-dollar investments in the United States because it is a pathway we understand. There are regulators that are known that we can work with, and we think we can license fusion in the United States quickly.
And is that that's like a medical device? That's what you see in hospitals, particle accelerators,
That's
right?
exactly right. That's exactly right. So, you know, it is one of the functions of our democracy, right? This is a delegated authority to the state. Not every state will regulate fusion this way, but for us, we feel like we have the certainty we need. But other big things, right? We need to be able to interconnect to the grid more quickly, right? If you build a power plant and you're waiting 5 years to be able to interconnect into the grid, that's a real problem. So we're very supportive of policies to expedite interconnection. The other cool thing, and Caleb kind of touched on this, is we don't have the big transmission constraints that other technologies are, right? Like you can site fusion where the load is. You don't have to string huge interstate transmission lines because that's where the resource is. It's like, well, if load is here, you can put fusion right next to it. And so in some ways, some of the fights that other industries have on like, how do we site these big interstate transmission lines, who pays for it, fusion kind of solves that problem, it avoids that problem. But we still need to upgrade and boost the grid, right? We need tremendous amounts of new electricity that will require to build grid out. So those are some of the things we're thinking about from a regulatory licensing perspective.
Anyone else want to comment on regulatory? Jack?
I'll just say, so we broke ground on our first commercial site this past summer. We knew we were going to build it in Washington State because our customer, Microsoft, said we want it in Washington State. Yep. The single driver, like the single biggest driver for where we put that plant in Washington was where we were going to have interconnect on a timeline that got us to deliver first electricity then by 2028, which was in that agreement. And there was one place in the entire state of Washington where that was possible, right? And so we need to move to a place where we're not making decisions on where we put our power plants based off of where there's one spot possible to get us interconnect in time. There's way more important considerations that we should be taking when we're thinking about those things. And I mean, I could go on and on about what that list is, but when I get to your question really quickly here is like, the two greatest impediments to scale for fusion are the supply chain and permitting. And permitting is not, you did a great job, Trent, like summarizing how amazing I am so grateful for our licensing environment vis-a-vis the NRC and the agreement states. It's a dream. But on the actual site permitting side, we're in the same pickle that every other generation source is in, right? And so if we end up getting the supply chain right, and we still lose scaling this new market to China because we simply can't get these things connected in time, what a sad story that will be. So that is still a major challenge.
That's completely under our control.
It is.
Anyway.
Yeah, I'd like to go actually a slightly different variant that goes to the supply chain more than the fusion machines, which are standards. At the FIA conference last year, Senator Warner...
Fusion Industry Association.
Sorry. Senator Warner made the comment that in the telco world, one of the reasons it scales is because there are standards. We know what the network protocols are. We know what the physical shape size are. We know what the power requirements are, the form factors, materials, temperature environments, those sorts of things. If we are going to have success in this market, we have to be willing to build those same sort of standards. Now, most of my background is in the IT cloud world, hence a lot of my AI examples. But if I walk into almost any data center in the world, I can tell you how much power there is in each rack, what the physical form factor is, where I need to build it. If I want to build something that consumes more than one power in a rack, this is the process that I follow. If I want to connect to the monitoring systems for control, networking for command, and interconnect systems to scale and stack them together, all of that stuff has been worked out with vendors and partners. And that's why that industry can scale. And that's, I think, the one other thing that could be very helpful as we look at the future of this is, I don't need to know how your fusion systems work. I just need to know how much power do you need to feed them, right? What size block do you want? Does it need a particular material? And whether it's myself or Vishay or TDK or anyone else who makes capacitors on the planet, that's what's going to get you scale.
So where is standardization necessary and appropriate? Caleb?
I'll make this very quick. Talking about, just to illustrate how difficult it is to get through the transmission queue. Right now, FERC's queue for interconnect, do you guys, so the US grid on the whole is about 1,300 gigawatts. Does anyone want to guess how many gigawatts are currently in the queue for FERC? Give me a number. 2,600? Oh yeah, okay, about that. Yeah.
It's a good guess.
Gold star.
It's about twice.
Only in Washington. Okay, I'm going to ask one last question and then open it up to the audience. So scale and international. How much does the international environment matter to what we want to achieve here on this panel? IAEA, anyone want to jump in on this? What does it matter what happens? Standards, we talk about regulation here, talk about regulation in Europe, very different, So what, and how does that fit into the equation of what we want to do here in terms of commercialization? Do you want to go first?
I'll go first. Yeah, excellent question. The IAEA and member states of the EU, a lot of countries are thinking about how do we license fusion. The UK was first mover. They decided to regulate fusion completely separately from fission. The United States followed suit. We are starting to see that develop in other G7 countries. Canada, notably, is exploring this, as is Japan. The industry will go to where they have licensing certainty. And so one of the things that you will hear very loud and clear from the industry is we need a risk-informed, right-sized licensing approach that doesn't keep us in the fishing camp, because the risks and hazards are fundamentally different. And so that is something that the Fusion Industry Association, other member companies are spending a fair amount of time thinking about. We will go as companies where we have market certainty, and that is a significant forcing function, I think, where this industry develops and deploys, and they will reap the benefits. And so getting that right is a really critical thing as other countries are thinking about how they attract this industry.
Well, I want to add too, because you mentioned the IAEA. So one of the roles that's been incredibly important that the IAEA has played for many years in the peaceful uses space is they created a milestones document of their own for countries that don't have nuclear power that want to pursue nuclear power. And it's sort of a list of all of the steps, arduous steps for nuclear that you have to take to develop a regulator and do all these things. But they literally wrote the book that pretty much is accepted globally for here's the gold standard for what you need to do to pursue this technology deployment in your country.
Fission?
For fission. So that exists, right? We recently found out that they are beginning the process of starting to do that for fusion. We've had, many of us on the panel and in the room have met with the DG Grossi, who is extremely enthusiastic about fusion. But they are at a place right now at the International Atomic Energy Agency where they are trying to figure out what their role is in a global commercial fusion ecosystem. And they don't know the answer to that yet. And so I think something that you touched on that's important with the UK and the US, we are, without doubt, the global leaders in what the future deployment of this technology looks like. These two countries, our regulators have been the ones who've said, here's what this looks like. Industry's on board, everybody's on board. I would love to see increased coordination and collaboration between our governments in communicating with the IAEA and in communicating with other countries and helping figure out what the path forward looks like so that we do actually see the regulatory harmonization that's been virtually impossible in the nuclear power space is entirely possible and should exist with fusion. And I think that the partnership that currently exists between the US and the UK is predominantly focused on fission, but there should be a lot more happening around this topic between the UK-US government.
And I'd put a little plug in if anyone from the State Department is watching. I think we still need an ambassador to the IAEA.
And we don't have an ambassador. As much as this administration loves nuclear and is doing so many fantastic things here, and fusion, in the critical moment we're in, it is a little mind-blowing that is a vacant position right now. We've got to be showing up at this moment for that agency.
Resumes. So, okay, so I think, did I miss, well, let's take some questions. If I've missed something that you all wanted to cover, just jump in, but let's see if there's some questions from the audience. Okay, this gentleman, the white shirt, and then I'll go to Daniel. Yeah, thanks.
Thank you. Jackie, I loved your comment that we need to move away from a reactive strategy towards trying something and accomplishing a feat that we have never done before. So I want to ask all of you why you think that a tax credit that is designed for that exact reactive strategy is the right vessel for fusion at this time. Trent, you mentioned that fusion is a technology that is unlike anything else before, but fusion supply chains have parallels with plenty of other technologies right now. Peak Nano is serving EVs for your capacitors in addition to fusion. And so while fusion is in this early stage, well, it can't supply that long-term kind of certainty needed in order to convince investors to actually expand their production. What is the use for a tax credit in funding directly fusion as opposed to funding, say, EV batteries and capacitors used for the grid that can then bleed over once fusion is at a stage where the technology is demonstrated and there is more confidence in the private sector?
Can I jump in on that first on 45X? So the reason 45X is such a great opportunity is because it already exists and it already is, it's already, other industries are already eligible for it. So you mentioned EVs, solar and wind. These are all, batteries. These are all things that are already reaping the benefits of this tax credit. This bill is actually just to add fusion to that, to just make this available to fusion, right? So that's, to us, that's kind of like the no-brainer first easy step. And it's actually been really amazing. So Yesenia from our team, who leads our federal affairs, has been sort of like the, running fastest out front on this. Like, guys, this is the easy thing to do. Let's do this. And so, it's been amazing because we've seen bipartisan support in both chambers that say, yeah, we get it. This makes sense. Let's try to make this happen. Of course, anybody in DC knows trying to find a vehicle to move it is the hard part, right? And so we're still hard at work on that. But that's really why that stood out as a sort of low-hanging fruit. Like, this is something we should absolutely be doing as soon as possible.
I think it's, ditto. I think it's also important to remember that there are different policy objectives. The original 45X tax credit was intended to onshore technologies that were invented in the United States and we lost, right? So from a supply chain security standpoint, from a owning your own infrastructure, from all the economic activity that generates from building up that supply chain here in the United States, the original policy objectives of 45X were, we've lost this, we need to bring it back through the tax code. For the Fusion 45X Parity Act, it's a different policy objective. We don't want to lose it in the first place. We want to ensure that the supply chain for fusion develops here where most of the fusion companies are. So I think it's the same policy mechanism with different policy objectives. So that's kind of how we think about it.
Thanks for the question. Daniel?
Hi, great panel discussion. Years ago, my colleagues and I at Sandia National Laboratories looked at the timescale for adoption of new energy technologies and everything from solar, wind, nuclear, oil, gas. And it appeared to be, on average, a rise time of about 15 years before any new technology became a significant fraction of the US energy market. And this trend went back decades. And so do we feel that, and so what I took away from that years ago was like, wow, if we had a working fusion reactor, Helion or CFS, whatever was successful 100% today, it would still be 15 years before fusion energy was a significant part of the US grid. You guys have outlined a lot of the barriers to that, the supply chain, the regulation, but the fact that it's not, doesn't seem to be technology dependent suggests that there's a lot of factors that have to be overcome. So I'm curious what your optimism is for being able to go faster than, say, 15 years.
Can I just, I'm just gonna say like a 2-sentence answer to that. I think that we find ourselves at a incredibly unique moment, because if you look at demand growth in the US, it's been relatively stagnant historically. So when you're looking at those other technologies from the past, you haven't had that ramp up. And right now you've got, this is what I meant when I was saying AI and fusion coming around at the same time. It just feels so meant to be, because you have this insane projected demand growth. And I think that's what's gonna really be the game changer for how fast you see fusion, commercial fusion deployed, because the demand is just gonna be through the roof compared to previous generation tech.
I think there's also an interesting switch that's happening. Is we tend to think of power as the power company is going to add a plant and have capacity, and I can add a new manufacturing plant. What has fundamentally changed is you look at Google, you look at Microsoft, you look at Nucor Steel, you look at some of these companies, they have an extraordinarily large power demand. It inhibits their ability to succeed. And these are organizations that produce more cash than any other company on the face of the planet. I read a stat the other day that Apple has more cash on hand than the US Treasury. These are people who can change the world fundamentally. If you look at the investors that are in these two companies, it's not the power game as we think about it. It's the greater technology infrastructure. And I think what we're going to actually see that most people aren't considering right now is that many of these tech companies will end up becoming some of the largest power companies because they can buy the land, deploy it, put it behind their factory, and then sell back to the grid. I actually think the model is going to flip on its head a lot over the next 10 years, and it will change the timeline for new power to get out there. And as with many things in that super high-tech world, they're also going to be able to make a ton of money on it and produce more cash. But in addition to the technology part of it, we are at a fundamental paradigm shift of who can deploy power plants. And I find that extremely interesting.
Yeah, it's a really good question, and I think learning a thing or two from history and how other technologies have hit the market as mature as they are at the time is something we have to be mindful of. I guess I would say a couple things. One, once this technology is invented, there are very few parts in a fusion machine. Like, it's not that complex. We think the industry looks very similar to like aerospace, you know, and if you can build the machine to build the machines, there's no reason why we can't be building several arc power plants all at the same time, even in the kind of early days. I think our challenges, which Jackie and Sean have touched on, are interconnection, right, licensing. But I think of like how we scale the industry, it's access to capital. And I think it is, to Sean's point, I don't think there will be a shortage of customer demand once this technology is available. So I think it is, how fast can you scale this industry? And I'm actually, I hope we're under 15 years, but I really do think that this is a thing that can scale more quickly. That, you know, I think a lot about SpaceX, right? Like, we kind of take for granted that like a few years ago, like a decade ago, like Elon was crashing a bunch of rockets off the coast in a barge, and we were like, commercial space, what are you talking about? And then like, he landed it, and again, and again, and now we kind of take for granted that commercial space is routinely servicing the International Space Station, that we have whole new capabilities like Starlink. And I think I draw some parallels to that industry and how I think we could scale more quickly once this technology is available.
Caleb, did you want to comment on the
Sure. I mean, I'll just make one point of the one slowing factor that you might most hear about is probably tritium use or helium-3 use, if you use that, because it's a very limited resource. There are ways that we can get it, but the way we expect a mature fusion industry will get their tritium is from fusion power plants, which will produce some excess amount. But that only happens so much per year. But there are ways around it. So it's not an innate limiting factor. What a fusion machine could do is just run deuterium-deuterium fusion, and then they can build their own fuel that way, costing a lot of energy to do it, but they can do that. They're also, the way that we expect to get our startup tritium, buying it from Canada, which has heavy water reactors that produce tritium naturally that way. And tritium decays into helium-3, which helium uses. And then the other way would be tritium-producing burnable absorber rods, which works in a light water reactor, which is how we get our tritium for the weapons program in the US. So
You need a whole panel on that.
Yeah.
So we have room for a couple of, one or two more questions, and then I'll ask if the panelists have any last thoughts. Any more questions? Yes, sir, up here.
Hello. When it comes to building supply chains, it seems like the debate is either we build it in the U.S. or it gets built in China. And I feel like there's a whole part of the conversation, like friendshoring or nearshoring, that I'd love to hear your thoughts on specifically. I've talked to a lot of investors, and they're obviously with the Trump administration, they're trying to get as much investment and things get built in the U.S. But a lot of times it's just not possible, or it's going to take way too much time. And I've had investors say, listen, at the end of the day, it's just not viable. We'll make a whole PR thing about it, but it's not going to happen. So I'm curious on like what you think the role of friendshoring here is for the fusion industry.
Sure, there's a lot of it available. If you want to check Appendix B of this, you can see where centers of fusion manufacturing are. I think some key opportunities can be cryogenics. So for superconductors, they need something to cool them down. Europe generally leads in cryogenics, and that is an area where China is fairly weak at the moment. High temperature superconducting tape as well, like leaning on Japan to produce that. The UK is so far the leader in fusion robotics from the work that they did at JET, the Joint European Torus. UK also has done a lot of work with fusion-ready steels. So that's an opportunity. And startup tritium we get from Canada.
So the inputs, yeah.
Yeah, and I just say, so my answer to your question is, it is so important, the friendshoring piece. I'm going to kind of speak on a more macro level about it, because I think what I want to avoid, I want the U.S. to run hard at things that make sense for us to run hard at, right? And so I mean, that's obviously very much part of the argument of like, let's focus on winning in the first place and stop trying to reshore things that the market's already gone. But in this instance, the UK is a huge partner there, and we need to be doing more with them on thinking through like, where does it make sense? Where are they most well suited to sort of run hard at supply chain issues? Where does it make sense for us? Japan, I mean, you name it. Like, I think that we have a ton of opportunities to partner with our allies around the world to make sure that everybody has a piece of this fusion economy and benefits from it, right? I also think that I'll just speak from real experience at Helion. One of the challenges we've been having is you'll find a vendor or somebody who you're working with in the UK or another country or whatever, and then it's not that long before a Chinese parent company comes along and says, ooh, that's a really good idea. We're just going to come and purchase this vendor. And that I bring that up because I just want to highlight the fact that like that is China's strategy, right? Like the big takeaway that we should learn from the mistakes we made with lithium-ion batteries as an example is this was not something that we like just kind of like messed up. Like we were trying to actually win the market and sort of the industrialization piece with batteries, and we failed. It was a strategic choice not to try to win that.
Yeah.
We chose not to. We said the innovation piece is what matters, and that's where the really high-paying jobs are going to be, and then the supply chain will take care of itself, but it's not what we're interested in. Yeah. And at the same time we made that strategic choice, countries across Asia made a very different strategic choice. And they decided to actually invest the large upfront capital and time that it takes to grow yield and create those successful manufacturing ecosystems, right? We have to make that choice with this. That's the difference. Are we going to learn from that lesson, or are we going to not learn from that lesson?
Thank you. Well, anyone want any parting thoughts? That was a good end note, but happy. Okay. Well, thank you so much, everyone, for coming. I really appreciate it. I learned a lot today, and thanks to everyone.
Thank you, Nadia.
Thank you.
Thank you.
And thanks, Hudson.